Lab 5, Choose Your Own Adventure. The point of this lab is to conduct and report on a lab experiment without having detailed instructions, by relying on the procedures and concepts we have learned so far. I have chosen to create a model of the solar system which I can use to predict the length of a year on a given planet. The model isn't perfect, but it's okay. This table shows the length of an orbital year in Earth years as given by this site, followed by the length of the first year that was reported by Python. If you round it off, you see that they're close, but not exact, and they're close enough to call it a decent model, but not a perfect. I also calculate the length of a Sidonic month, which according to Wikipedia is the average period of the moon's revolution with respect to the line joining the sun and Earth. Also according to Wikipedia, this is 29.53 days. My model is unstable, but eventually settles into that length being around 28.89 days. The instability and inaccuracy are due to my assumptions. My biggest assumptions are that this model does not account for the outer planets or other stars or anything else, and also that satellites other than the Earth's moon do not influence the motion. I also assume that the planets all orbit in the same plane, which actually isn't that bad of an assumption. Further contributing to error, I use simulated position and speed data, and I also make some graphical simplifications that don't actually affect calculations. My model is based off of Newton's universal law of gravitation and Newton's second law, and I make sure to remember that Fnet is the sum of all forces acting on an object. The structure of my code is simple. I initialize my objects, and then in my while loop, I find the net forces on all planets, and then I update each planet's velocity and position, and then I check for years and months. The actual implementation is a little bit tricky, so I'm going to start by running my model to see if it works. And we see planets, 4 planets going around the sun, and this one is the Earth and the Moon system, and it looks like it's rotating out of control, but actually that's just the Moon orbiting around the Earth, and you can see that because the trails are not exactly on top of each other. So this implementation, though, I use a class. If you don't know what that is, just think of it as a collection of attributes and functions. So each of my objects has some things useful for updating, useful for orbit tracking, and useful for the graphics. It also has a findFgraph function, which calculates the force of gravity for a given source and returns 0 if the source is the same as the object. It also does an update using Newton's second law and a position update. This findAngle function tracks years. A year is the time it takes a planet to orbit around the sun, and this can be tracked by seeing when the angle between the x-axis and the planet's position equals the initial value for that angle. So if that angle is passed, I increase the number of orbits, and then I account for the fact that it does not mark exactly when the planet crosses over. This simply takes the ratio of the overshoot over the total distance, and so I take the time minus that overshoot and divide it by the number of orbits to get the length of time that it took for the year to pass. I then convert that to years and print out the results. That's the meat. Let's get to the easy stuff. I set up a scene. I set up the sun, which is just simply a sphere, and I attach a mass and a string to it. Then for initialization, I create a sphere object for drawing, and then transform it into a planet object by passing the sphere into the planet initialization and overriding it with the same name. I take the mass, position, and velocity data given by my website, and I put position and velocity as vectors to avoid type error. I googled the moon's data and set it up, and these are for month calculations. Then I set up the gravitational constant and the time step. This findFnet function tracks the net force on an object, and this takes care of the months and some formatting stuff. Now, let's see the length of stuff, and it tells us how long it took the moon to orbit, how long it took each planet, and there's a full Earth here. So, that's nice and all, but what about the months? Months, it measures, like I said earlier, the angle between the Earth-Sun vector and the Moon-Earth vector. And I do that by calculating the unit vectors for the Earth and the Moon, and then comparing them to find the correct angle, and then doing the same calculation for the year calculation. The value is off because the whole model is off because I use weird initial position. It's most noticeable in the month because the month has the shortest period. In conclusion, modeling stuff in Python is fun. You just need to know your goal and your assumptions and simplifications, and most of all, just don't be afraid to experiment. Thanks for watching.